Okay, so experiments involving finding out how much water of crystallization there is in a compound or things related to that are very common. So for example, we might be talking about a compound like this, which has got calcium chloride, so calcium ions and chloride ions in a lattice, but the lattice also contains water molecules as part of the structure. So this is water incorporated as part of the solid, and this whole thing, remember, is called hydrated calcium chloride. And this, the water that's locked up in the crystal, is called water of crystallization. And what's important is that for a given ionic compound, there is generally a fixed amount in terms of the relative number of moles of water to the moles of the ions in the crystal lattice. And that water can be removed by strong heating. So if you heat it up, you can get a version of the compound that has no water of crystallization, which is then called the anhydrous compound, so anhydrous calcium chloride. And the water of crystallization is removed as steam, which just boils away. And of course, if you do that in an open container, the mass goes down because the steam disappears off into the air. So you need to practice doing the calculations based around those kind of experiments, but also sometimes they will present you with the results sort of in the form of raw experimental results, so that you have to make sure you can extract the numbers from them. So let's look at a couple of examples of that. And again, the best thing to do is, when I put the example up here, then pause, have a go at the question, and then go through the video, see if you got it right. Okay, so here's an example of the sort of thing you might get if they're actually giving you experimental data rather than just the numbers that come out of it. So this is the sort of experiment that you do, which you remember we did one of these in class. So you take a porcelain pot called a crucible, and the first thing you do is you weigh the crucible when it's empty. So you've got the mass of the crucible here. And then you put some of your hydrated compound into it, and you weigh it again, so you get the mass of the crucible plus the hydrated compound, which will obviously be bigger. And then you heat it. Usually you keep the lid on for a bit until it's boiled away, and then you partially remove the lid or whatever, but without going into the details, that the main thing is that you then, having heated it for a while, you let it cool and you weigh it again. And the mass will have gone down because some of the water of crystallization will have been removed. But the point is that you can't tell whether all of it's gone or just some of it. Mass has gone down, so you know some of it's gone, but some of it could still be there. And that's why we've got these repeated readings here, okay, where you keep on heating it, cooling it, weighing it, until the mass stops changing. Because only when the mass stops changing can you be confident that all of the water of crystallization has gone. So that's what's happening here, that we start with the biggest mass, we heat it for a bit, the mass goes down, we then heat it some more and the mass goes down some more. So you know at that point not all the water of crystallization had gone. Maybe it has now, but again you still can't be sure. So you heat it, cool it, weigh it a third time, and this time the mass stays the same. So in that case, you say you've reached constant mass. And that's what it means by heating to constant mass, that you heat it until the mass stops changing, and then you can be confident that all of the water of crystallization has gone. So your mission is to take those raw data and first of all complete the table with two numbers. So I want you to add into that the mass of water lost, so the total mass of water lost during the heating by the time you've reached constant mass at the end, and the mass of the anhydrous compound. also in grams. So you've got two numbers to put in there, and then using those numbers, see if you can do the calculation, find the value of x. So have a go at that now, and then you can unpause the video and see if you got it right. Okay, so let's start with these masses then. So the mass of the water lost. So before we heated it, we had this. We had this 61.38, because that's the mass of the crucible plus the hydrated compound. At the end, of course, the crucible is still there, but the water is gone. So this final mass here, after we've heated to constant mass, is the crucible plus the anhydrous compound. And so the difference between those two numbers is the mass lost. So that's equal to 61.38 minus 57.20, which is 4.18 grams. The mass of the anhydrous compound itself is this mass at the end, because that's the anhydrous compound plus the crucible, and now we've got to take the crucible away. So it's 57.20 minus 49.88. Okay, because that's just the crucible on its own. If we take away that number from the crucible plus the anhydrous compound, obviously what's left is just the anhydrous compound. So that's 57.20 minus 49.88, which is 7.32 grams. Okay, so equals 7.32 grams. Okay, so those are the two numbers that we're now going to use and carry through into the next part of the calculation. Okay, so these are the numbers we've got, and x is just the ratio of the number of moles of water to the number of moles of magnesium chloride. So in other words, if there were 9 times as many moles of water as there are of magnesium chloride, that number would be 9. That's all x is. So really all we have to do to work out what x is to work out the moles of water and the moles of magnesium chloride, and then divide. X is the moles of water divided by the moles of manganese chloride. So that's the method we're going to use. So we're going to turn that into moles. Is mass over mR, which is 7.32, and the mR of manganese 2 chloride is 125.9. Make sure you don't get manganese and magnesium mixed up. Okay, Mn is not the same as Mg, so you're obviously going to get the wrong MR if you look up magnesium instead of manganese. And that comes to 0.05811 moles. And then we do the same for the water. So again, moles is mass over mR, which is 4.18 over 18.0 is the mR of water, and that comes to 0.2322 moles. Okay, so there are more moles of water than there are of manganese chloride, which tells us that x is going to be bigger than 1. But we can work out what x is, because x is just the ratio of moles of water divided by moles of manganese chloride, which is 0.2322 over 0.05811, which comes to 3.99, but we're expecting it to be a whole number, so obviously that's approximately equal to 4. So the answer is that manganese chloride crystallizes as the tetrahydrate MnCl2.4H2O. Another thing they might ask you to do while you're doing a question like that is a percentage uncertainty, percentage error kind of thing. So they might ask you something like, what's the percentage error on the mass of water? So generally they would tell you what the percentage error on a mass reading was, although you can kind of work it out as we discussed when we looked at percentage errors. But let's say that each mass reading has an uncertainty of 0.005 grams, and that's the minimum uncertainty you can have if you have a 2 decimal place balance. So the crucial thing to realise is that to get the mass of water you had to make 2 mass readings, right? Because remember how we worked it out, it was the mass before heating, crucible plus the compound, and then the mass after heating, the crucible plus the compound. So you have 2 mass readings. And so you have to add up those 2 uncertainties. So that means that the percentage uncertainty is 2 times 0.005. Okay, so 2 lots of the individual uncertainty divided by the value measured, and the value measured for the mass of water is 4.18 times 100, which is 0.24%. Okay, so that's a good example to test whether you've picked up that idea of if a number you determine depends on more than one reading, you've got to add up the individual uncertainties when you calculate the percentage uncertainty like that. Okay, here's the other kind of water crystallization problem that you commonly get, where this time we know the number of waters of crystallization, but we don't know the identity of part of the formula, in this case the metal ion that's paired with the 2 nitrate ions. So this time I've given you the numbers, you haven't got to extract them from data, but obviously you might have to do that in the same kind of way. But we start off with 7.24 grams of this hydrated compound, we heat it to constant mass, and the mass decreases to 4.19 grams. And your job is to figure out what the identity of element X must be in order for those numbers to make sense. So again, have a go at it with the video paused, and then run it again to see if you got the answer right. Okay, so place to start is to find the difference in the mass, because that's the mass of water lost. So you get the mass of water driven off by heating is 7.24 minus 4.19, 3.05 grams. And so we can turn that into moles of water is mass over mR, which is 3.05 over 18, and that's equal to 0.16944 moles. Notice, as usual, I'm carrying too many significant figures here. In fact, I'm going to use the number that's still in the calculator, which has even more significant figures, just to make sure we don't get any rounding issues. So that's the moles of water, and this number 6 in the formula tells us that the moles of the hydrated compound is 1/6 of that. Okay, because there are 6 waters for each one of those. So we can write down that the moles of XNO32 is the moles of water divided by 6. And if we divide that number by 6, we get 0.02824 is that number. And we've now got everything we need to get the MR of this compound, because we know the mass of it. Okay, that was the mass of the anhydrous compound, and we now know the moles of it, so we can do that the MR of XNO32 is mass over moles, which is 4.19 divided by 0.02824. Which comes out to 148.4. So we know the MR of the compound, and if we take away the MR of the two nitrates, that will leave us with the relative atomic mass of X, which will tell us what it is. So 2 lots of NO3 has an MR of, well, 3 oxygens, 316s are 48, plus 14 is 62, and 2 62s are 124, so 124. So that means that the AR of X is the total 148.4 minus 124.0, which is 24.4. So then you just go to your periodic table and you find the appropriate element which has an MR closest to 24.4. I say appropriate element because you've got to make sure that it makes sense. In other words, it's got to have a 2+ ion to balance the two nitrates out to give you that formula. So there's no point choosing like a group 1 compound or a group 3 compound, because that wouldn't work. But that's fine, because the one that comes closest to that is magnesium, which is 24.3, and that is in group 2, which fits with that formula. So that tells you that it's magnesium is the element, so it's hydrated magnesium nitrate.